Welcome again to this presentation. Today we are going to discuss a new series of questions, which are questions and the answers regarding the chemical equilibrium. Let's quickly start on question number 1. Question number 1 is saying consider the reaction which is PCl5, which gives PCl3 plus chlorine 2. So all of them, they are gas. You have gas here, and you have gas here. Where the initial amount is 1 mole of reactant in 1 liter. So that means you have 1 mole of reactant in 1 liter. So the molarity is equal to 1 dividing with 1 liter. That means you have 1 molar as the concentration of each of the reactant. We have at the initial amount of reactant, you have 1 molar. Then they are saying at equilibrium they measured and they obtained 0.135 mole of PCl3. So at equilibrium they measured and they find only this one. The others they didn't calculate. So this they have given only this the concentration of this one at equilibrium. So we don't have the concentration of this one at equilibrium, and we don't have the concentration of this one at equilibrium. Then they are saying how much chlorine 2 and PCl5 are present at equilibrium. That means at equilibrium we need to find the concentration of PCl5 and the concentration of chlorine, and this one was given. Let's quickly go to the answer. What you know is that initially we have only the reactant are present, so we don't have the product. When you are at initial step, so we have only the reactant, we don't have the product. So you can set the initial change and equilibrium. You can have the initial change at equilibrium, and you are here at initial. Initially, we have only the concentration of the reactant and we don't have the product. So actually the three species that we have the PCl5, phosphorus pentachloride. We have also this one and we have this one. But the initial step, we have only this one, the reactant. Here, and initially you have only this one, which is equal to 1 mole. That means you have 1 mole. This 1 mole comes from 1 mole dividing with 1 liter, then you get 1 mole. So the concentration of PCl5 at initial state, we have 1 mole, and the product are not there initially. So we put 0 for the PCl3 and chlorine 2. Because initially you have only the reactant. So now what is the change? The change is occurring and the reactant are transformed into the product. That means we have this one transforming into PCl3 and chlorine 2. So the reactant, the change is that the reactant are transformed into the product. That means this PCl5 will be decreasing while we will be forming PCl3 and the chlorine 2. So that is where we have the change. In the change, then we say negative X, because here we are removing the concentration of PCl5, the concentration of reactant, and we are forming X, the concentration of the product. So the change is that the reactant are removed and the product are formed as you can see. Then after the equilibrium is established, then at equilibrium we have 1 minus X, here we have 0 plus X, and here we have 0 plus X at the equilibrium. Equilibrium is established, and then we have the equilibrium concentration. Here we have 1, which is the initial molarity, negative the one which goes to form the product. Here we have the one which forms the product, and here we have the one which forms the product. So now what do we have? We have here in the equation that they measured and obtained 0.135 mole of PCl3. That means at equilibrium you have this one. This one was given, and it is equal to 0.135 mole. So the PCl3 was given at equilibrium, is equal to 0.135 mole. So of course this X is equal to this X also. That means also you can find here the concentration of chlorine at the equilibrium. See, that means the X is equal to PCl3 is equal to chlorine 2 is equal to 0.135 mole. Then what will be the concentration of PCl5? In this case we take 1 minus X, which will be equal to 1 minus 0.135 mole. In this case now we have all the concentration that they have asked to determine. So we have here PCl3, which is equal to chlorine 2, which is equal to 0.135 molar, and you have also PCl5, which is equal to 1 minus x, 1 minus 0.135 molar, and you have 0.865 molar. Let's move to the second question. The second question is asking the same constant the reaction. We have PCl3 plus PCl2, which gives the PCl5. Of course, all of them, they are gases. That means you have the homogeneous. So in which the equilibrium concentration reactant, so we have the equilibrium concentration of PCl3 we have, which is equal to 0.5. We have also the equilibrium concentration of chlorine 2, which is equal to 0.07 molar. Now they're asking what is the equilibrium concentration of the product PCl5. So they're asking to calculate this one. Now they have given the equilibrium constant. So here we can use the formula for equilibrium constant to determine the concentration of PCl5 at the equilibrium. So this is the equation. Now what is the Kc, which is the constant? The Kc is equal to concentration of the product raised to the power of the stoichiometric coefficient, but here we are raising it to 1. So here also we're dividing with the concentration of PCl3 raised to 1 times the concentration of chloride raised to the power of 1, because here it is we have only stoichiometric coefficient is 1. Here we put 1, so 1. So you can put it or not put it. Then we can have the PCl5. So that means the concentration of PCl5 at equilibrium equal to Kc times this, the concentration of this one times the concentration of this one. So we have the PCl5, which is equal to Kc times the concentration of chlorine times the concentration of P-chlorine times the concentration of chlorine. So then we can replace the values. The Kc was given as 96.2 molar. So it was given 96.2 molar negative 1 times 0.05. So that means we have the concentration of PCl3. It was given as 0.5. And you have also the concentration of chlorine as 0.07. If you multiply these values, then you get 6.367 molar as the concentration of PCl5 at the equilibrium. Go to question number 3. Question number 3 is saying, for the following reaction A plus B, which gives C plus D, the equilibrium constant is 49 at a certain temperature. If 0.4 mole of each A and B are placed in a 2-liter container at that temperature, what concentration of all species are present at equilibrium? Here they're asking what concentration or all species are present at the equilibrium. So which concentration is present? A, B, and C, D at the equilibrium. So we use the initial change equilibrium. So let's see the equation that we have. We have A plus B, which gives C plus D. We have also the initial concentration, because here we have 0.4 mole of each A. That means we divide it with the volume of the volume that was given is 2 liter. That means the concentration is equal to 0.4 dividing with 2 liter. Then you have the initial concentration of A, which will be equal to 0.4 dividing with 2 liter. We have also initial concentration of B, which will be equal to 0.4 dividing with 2 liter. So here we have the initial concentration. That means initially C and D, they are 0, they are no longer there, because we are not yet forming the product. Then the change that will occur, that means this A will be removed, B also will be removed to form C and D and D. So then, told you that no product are present initially. So we have the initial change equilibrium. We have also the A, B, C, and D. So initially we have here 0.2 molar of A, 0.2 molar of B. Then for C, we don't have, we have 0.2 molar of A, 0.2 molar of B, and here 0. Then the change, that means we replace minus x, because A and B are removing and C and D are forming. That's why you can see for C and D we are putting plus x. Then at equilibrium, that means we behave 0.2 minus x, 0.2 minus x, and here we get 0 plus x, 0 plus x. That is what we have at equilibrium. Then we know that the K, which is the equilibrium constant, will be equal to C times D over A times B. So concentration of C times concentration of D over concentration of A times the concentration of B. That is the value of Kc. Then if we can replace here, what is C? C is X. What is D? D also is X. and what is b? 0.2 minus x, and a is equal to 0.2 minus x. Then we have replaced the values, the unknown that we have, then we can solve for x. But remember here we have 1, 1, and 1 as the geometric coefficient that we did want to include them because it is 1. But if it is not 1, make sure please you are including the stoichiometric coefficient in the calculation. Let's continue by solving this equation. So we have also the equation that we have developed, that means x times x, that means x squared, dividing with 0.2 minus x, 0.2 minus x, that means 0.2 minus x squared. So then the KC was given, that is 49, so the term here remain. So here it is square and here it is square, and we can introduce the square root on both sides. So we introduce square root of 49, here also square root of this term. So then we have the 7, this is 7 equal to x over 0.2 negative x. So then we can do rearrangement, x is equal to 7 times this one. So we have x is equal to 1.4 negative 7x. So then we can get the value of x. So we get that x is equal to 1.4 over 8, which is equal to 0.175 m. So then after getting the x, so we know that x is equal to c is equal to d. Then what is a and b? So remember what is a and b in the table. We have seen that the a is equal to b is equal to 0.2 negative x, which is equal to 0.2 negative 0.175. Then we get 0.025 more. That was for question 3. Let's move to question 4. What is question 4 is saying that for the following reaction A plus B, which gives C plus D, the equilibrium constant is 49 at certain temperature. Now they are changing the number of mole. It is the same as the previous equation, but here they are changing the number of mole. They are saying 0.6 mole of A and 0.2 mole of B are placed in a 2-liter container and allowed to reach equilibrium. They are asking what is the equilibrium concentration of all species. Here also we do the same as we have done for the previous exercises. We determine the concentration of species initially. For A it will be 0.6 dividing by 2, which is equal to 0.3. For B it will be equal to 0.2. Here 0.2 more dividing with the volume 2 liter, then we get 0.1 more. Initially, that is what we have. C and D, they are not there initially. So then we complete our table. So we know that A will be equal to 0.3 initially, and B will be equal to 0.1 initially, and C and D, because they are product, they are not yet formed, no product present initially. Then we will behave a change here. The A will be removed, B will be removed, and C will form, and D will form. So we do minus x for A and B, and then plus x and plus x for C and D. Here then we can determine the equilibrium. Here we have 0.3 negative x and 0.1 negative x and x and x. That means 0 plus x and 0 plus x. That is what you have at the equilibrium. So then we know that the stoichiometric coefficient is only 1. Here then we have the Kc, which is equal to concentration of D times concentration of C dividing with concentration of A times concentration of B. Here we are having Kc, which is we are replacing here the value that will be x times x over 0.1 minus x times 0.3 minus x. So let's proceed to solve the equation. So we have this one. We can do after doing several rearrangement. You can see we are using several rearrangements so that we can get here a quadratic equation. So at the end we get this equation. After different rearrangement, and at the end you are going to get the equation which say 48x squared is negative 19.6x plus 1.4 equal to 0. Now we are going to solve this quadratic equation. So hope that you remember in secondary school how to solve the quadratic equation. This is, you are going to refer to your mathematics. Here I will check whether you understand well mathematics, because here we need to solve the quadratic equation and get the answers for the two roots of this equation. Let's see. So this determinant is equal to b squared negative 4ac. What is b here? This term, that is A, that is B, and that is C. That means we can get b square, that is negative 19.6 square, that is b square, because b is this one, minus 4ac, that means a is 48 here and c is 1.4. Then we will get the determinant is equal to 101.92. We determine the square root of the determinant, we obtain 10.1. Then the first roots, the x1 is equal to negative b minus the square root of the determinant over 2a. Then we replace the values, so we get 0.099 molar for x1. We also determine the x2. This will be equal to 0.309. But both of them, they are positive. So which one do you choose as the right roots, or the right answer for this, as the solution for this equation? We need to choose, and by choosing we need to use the logic, because if one is negative, it's okay, you just reject the negative concentration, but here all of them, they are positive, so we need to choose based on what we need to choose wisely. So now, what were the initial concentration? The initial concentration, it was 0.1 molar. If then the initial concentration is 0.1 molar, you cannot form product which are more than the reactant. So it cannot be the reactant are consumed to give the product, and it cannot be more than the initial reactant present. That means this X, which is the product which is formed, cannot be more than the reactant present. That means this X2, which is higher than 0.1 molar, which is the reactant present, in this case, this external root. In this case, we rejected this root. That means the C will be equal to D equal to 0.099 molar. That is the concentration of C and D. Now, what will be the concentration of A? The concentration A is equal to 0.3 negative X. That means 0.3 negative 0.099. What will be the concentration of B? Is the same. We take 0.1 negative X, which is equal to 0.1 negative 0.099. Then you will get 0.0001 molar. So here the trick was just to solve for the quadratic equation. I know that's where the students, they are roasting. So if you give them the question which require to solve the quadratic equation, I know most of the students, they are raising in mathematics, so they don't understand the mathematics. So it's very problematic. But the problem is not chemistry. The problem is just the simple mathematics that you have covered in secondary school, how to solve the quadratic equation. Let's go to question 5. Question 5 is saying, suppose a following reaction is given, starting with 0.5 mole of HI in a 5 liter flask. Calculate the equilibrium concentration of each substance, and here we have K is equal to 0.060. So the trick is the same. So we are going to have this equation, and here you can see that we have the stoichiometric coefficient. Here we have 2, so we need to use these 2. Here we need to pay attention. So the initial concentration, we take the number of mole dividing with the volume, 0.5 dividing 5, then you get 0.1 mole. Then we use the initial change equilibrium relationship. Here initially you have only HI, which is equal to 0.1 molar. The others we have 0. Then for change here, because we have 2 HI, 2 moles, that means it will be negative 2x. 2x will be removed to form the product, and here X product will be formed, and the X product will be formed, because here you look on here the number of mole, and here the number of mole. Here we have 2. That means we have negative 2x to form, that will be removed to form the product. The reactant are removed while the product are formed. Then here we have at equilibrium, which is 0.1 negative 2x, the initial minus the change. Then you have x and you have x. Then we can have the Kc. Kc was given as 0.16, then it's equal to x times x over 0.1 negative 2x squared. So that is what I was telling you, that we need to raise to the power stoichiometric coefficient, and also here we need to use this coefficient. Don't forget to use this one, and also to raise to the power of stoichiometric coefficient. Let's then solve the equation. We have this one, we have this one. So we are doing just simple rearrangement so that you can get a quadratic equation. Let's see whether, yes, this is the quadratic equation that we have, which is equal to negative 0.9 0.36x squared negative 0.0064x plus 0.00016 equal to 0. Then you determine the determinant. After determination of the determinant, we determine the square root of the determinant. We get the x1 which is equal to 0.01, and we get x2 which is equal to negative 0.017. This is the concentration cannot be negative, then we reject the x2. That means the x1 will be equal to 0.01 molar. So then x1 is equal to concentration for hydrogen is equal to concentration of iodine is equal to 0.0999. So here they have rounded to 0.01, but it is in reality 0.099. But if you can write this one 0.01 or 0. This one, all of them they are good answers. So then HI, remember, is equal to 0.1 minus 2x. We get this from the table at equilibrium. Then we get also the HI, the concentration HI, which is equal to 0.08 molar. That was question 5. Let's go to question 6. So now, hope that you are getting something. You have the reaction. The initial concentration of the reactant is 0.1 molar. Then they're asking what is the equilibrium concentration. The Kc was given, so we are going to do the same. So that we have 0.1 molar for the reactant, and in the product we don't have the concentration because we are still initially we have only the reactant and we don't have the product. Then here we are going to have minus x, and here we are going to form 2x because here we have 2, we form 2x, and then here we have 0.1 negative x, and here we have 2x, and then we solve for Kc is equal to x, here 2x, but don't forget to raise the power to the stoichiometric coefficient. Yes, we have raised the power to the stoichiometric coefficient. That means the 2x over 0.1 minus x. Please make sure that you don't forget this one. If you have the stoichiometric coefficient, make sure that you don't forget. Students always forget that, but make sure that you are using that the stoichiometric coefficient. So let's go to this. The answer for this question, we have the Kc. So we are doing the rearrangement. We have the 4x squared over this one. So these are simple rearrangement that we are doing. Just simple calculation, so that you can get the quadratic equation. The quadratic equation that we have is 4x squared plus 0.36x negative 0.036 is equal to 0. Then we determine the determinant, and we solve for the roots, the two roots. So of course we need to reject the one. So we reject this one with negative. The one with 0.15 is negative. That's why it will be rejected. That means the x2 will be equal to 0.06 molar. So the NO2 will be equal to 2x. Then we take 0.06 times 2, it will be 0.12, and then N2O2 will be equal to 0.1 negative x at equilibrium. Then we can also do the same by taking 0.1 negative 0.06, then you get 0.04 molar. The next question is question number 7. Question number 7 is saying Kc is equal to 65 for the reaction. So the reaction was indicated. The following concentration detected in a mixture 0.5, 2.8, E is equal to 3.4. So that means we have the concentration in the mixture, but they are not telling us whether they got them at equilibrium. Then they're asking the system at equilibrium. That is what they're asking. We need to determine whether the system is at equilibrium. If not, if the system is not at equilibrium, they're asking in which direction must the reaction proceed for equilibrium to be established. For this kind of question, when they are asking whether the reaction is at equilibrium or not, you should calculate what you call the reaction quotient. Before the equilibrium and after the equilibrium, you calculate the what you call reaction quotient. The reaction quotient is calculated the same way as the equilibrium constant, except that for the reaction quotient, we are using the concentration which are not yet reaching the equilibrium. Then after getting this concentration, to verify whether the equilibrium was reached or not, you need to compare with the equilibrium Kc, the equilibrium constant. But here they are asking, is the system at equilibrium? The Kc, the equilibrium constant, was given. So here we need to calculate the reaction quotient to see whether it is equal to Kc. Because at equilibrium, the reaction quotient is equal to Kc. Or the reaction quotient is equal to the equilibrium constant. Let's see, we have all the values. We know the Q is the reaction quotient will be equal to the concentration of hydrogen times the concentration of iodine divided with the concentration of Hi, but we are raising to the power of stoichiometric coefficient. But what you need to understand is that there's a concentration that we are putting in the equation, H2, E2, and Hi. They are the concentration not at the equilibrium state. So here, we are not yet at the equilibrium state. That's why we are talking about the reaction quotient. When this reaction quotient is equal to the Kc, that's where we are. We are now at equilibrium. In that case, we are at equilibrium. So if you calculate, you see that the Q, which is the reaction quotient, is equal to 38.08. It is less than the Kc. That means the reaction is not yet reaching the equilibrium. If it is equal to the equilibrium, if the reaction quotient is equal to the Kp or Kc, the constant, in this case, we have what you call the equilibrium. But if it is less or higher, you don't have the equilibrium. If it is less, that means you are not yet reaching the equilibrium. If it is higher, if Q is higher than the equilibrium constant, in this case, we are above the equilibrium. So the system here, the system is not at equilibrium because the Q is less than the reaction quotient is less than the equilibrium constant. If the Q is higher than the equilibrium constant, again, the reaction is not at equilibrium. A reaction is only at equilibrium when the reaction quotient is equal to the equilibrium constant. Now they are asking in which direction. That means if the reaction is not yet reaching the equilibrium, the reaction will proceed to form the product until the equilibrium is reached. For the equilibrium to be established, that means the value of this one has to increase so that it is going to be equal to 65. That means to increase this value, you need to increase also the concentration of hydrogen and the concentration of iodine, or decreasing the concentration of the Hi. That means here you are going to have more, the reaction is going to proceed by forming more hydrogen and more iodine until the equilibrium is established. So that means the direction of the reaction is from left to right. So some Hi, or the reactant in this case, will react or will decompose to form the hydrogen and the iodine so that the equilibrium is reached. That was question number 7. It's somehow theoretical because it was not requiring the calculation. Let's see question number 8. I think also there is no calculation for question number 8. It is saying write the relationship between Kp and Kc for the following reaction. The reaction were given. They have so around 1, 2, 3, 4, 5 reaction. That to write the equilibrium expression. The Kp equilibrium expression at constant pressure, and the Kc at the Kp for the pressure and the for Kc for the concentration. So when you see the gases, so we use the Kp because we have the pressure. But when you have Kc, that means we have the liquid, which is the concentration. So let's move. So here we have all of them, they are gas, right? And remember, we have seen the relationship between Kp and Kc. What is that relationship? So let's first see the equation. This is the equation. What is the relationship between Kp and Kc? So Kp is equal to Kc times the gas constant times the T, which is the change, which is T, the temperature in Kelvin, and the delta N, which is the number of mole. Mole of product minus the mole of reactant. So then what is the change in number of mole? Here we have 1 mole and here we have 1 mole. That is 1 plus 1. That is 2 mole minus 1 mole for the reactant. Then you have 1. The change in number of mole is 1. Then here we have the Kc81. That means we have Kp, which is equal to Kc RT. That's the expression. For the second one here, the chain number of mole you have 2, then minus 4. That means will be here, the chain number of moles will be equal to -2. Then here we put -2. Then you have Kp is equal to Kc Lt power -2. So here also we have this one. So the chain number of mole is 2, -2. That is means 0. The Kp that is equal to Kc Lt power 0. So if you power 0, that means we get 1. So that means Kp is equal to Kc. The next one was asking the water giving the hydrogen and oxygen. Here also we have 3 moles minus 2. That means the change in number of moles will be 1. So the Kp will be equal to Kc Rt power 1 or Kc Rt. The last one is this one, and it is also the chain number of mole you have 2 minus 3 minus 2 plus 1. Then you have -1. Here we have the Kp is equal to Kc Rt power -1, which is equal to Kc over Rt. So we are reversing this one. So they were asking the expression, and now we have the expression for the relationship between Kp and Kc. Question number 9. Question number 9 is saying consider the reaction, this one, in which the equilibrium constant Kp for the reaction is this one. So the Kp was given. What is the numerical value of what is the numerical value in mole per liter of Kc for this reaction at the same temperature? Now they want us to determine the Kc at this temperature. So let's do it quickly. So we have here the equation, and here we have the Kp. This is the Kp that we have. We know the Kc, the Kp was given, but they are asking the Kc. So the Kp is equal to Kc, the chain number of mole is 2 plus 1, that means 3 minus 2, that means we have 1. That means Kp is equal to Kc times Rt power 1. Like we can replace the value. This one we have. The only unknown that we are having is Kc, because the gas constant we know, the temperature we know. But remember, the gas constant can be expressed in different units. That's what I want to show you. The temperature is in Kelvin, but the gas constant has different units. We need to choose which one to use. So choosing on which gas constant that you're going to use depend on this unit. Here you can see we have kilopascal. So that means we need to use the gas constant which has kilopascal. So let's see how the gas constant we have derived, how the gas constant is obtained. So PV is equal to nRT. That means gas constant equal to PV over NT. So here at STP we have 1 moles. The temperature is 0 degrees Celsius. That means that 273 Kelvin. And what is the volume occupied by 1 mole? 1 mole at standard temperature and pressure, 1 mole of a gas occupies 22.4 liter. So then the pressure is 1 atmosphere at standard state. Then by replacing, we will get that the gas constant equal to 0.082 liter atmosphere per mole Kelvin. But here we don't have a kilopascal. That's why we need to change it to kilopascal. So we know 1 atmosphere is equal to this 1 pascal. Then we can replace this 1 atmosphere with pascal. So we replace this atmosphere with pascal. Then after replacing, we get the liter pascal per mole Kelvin. But here by having pascal, you can convert to kilopascal by dividing by 1000. Then you get 3.31 liter kilopascal per mole Kelvin. So we can use then this one to calculate the Kc. So we can also convert this one to 1 pascal is equal to Newton per meter square. Then you can replace here pascal by Newton per meter square. Then we can also replace the Newton by its value. We know 1 Newton is equal to kilogram meter per second square. Then we have also the gas constant, which has air times liter kilogram meter per second square per mole Kelvin. So what is this one? So we can convert this liter to meter cube, so that here the meter and meter they cancel. We know that the changing for liter to meter cube we divide with 1000. So we have also here kilogram meter square, kilogram meter per second square over mole per kilogram. So then after we are simplifying, if you can see, kilogram meter square per second square, that is joule. Kilogram meter square per meter square, kilogram meter square, because here we have kilogram, the meter cube, then we cancel with this meter, because we are getting 10 power -3. So we are changing the liter to meter cube. So in this case, we have kilogram meter square per second square. So we have kilogram meter square per second square. That means that is joule. So we have another unit of 8.313 joule per mole Kelvin. So they are just different units that you can express the gas constant. So depending on the question that you are having, you can choose which one you are going to have. Let's see. So the preferable one is this one, which is equal to liter kilopascal per mole Kelvin. So then you can replace it the values. Then we will be having K is equal to 3.09 times 10 power negative 7 mole per liter as Kc in that was the requested to calculate in this exercise. So let's continue. For question 10, which is the last question, conduct the reaction, predict the effect of each of the following change on the amount of ammonia present at equilibrium. So if you force more ammonia into the system, that means we are forcing more hydrogen in the system. So that means we are adding the reactant. Adding the reactant, that means we shift the reaction toward the formation of the ammonia. Another one is saying if we remove the ammonia, what will happen? If we increase the temperature, what will happen? If we lower the temperature, what will happen? If we add the catalyst, what will happen? Then the question also has B. B is saying given the reaction 1 and reaction 2 below at equilibrium in a closed container at this temperature, predict the effect of increasing the pressure by decreasing the volume in each of the reaction. So let's move quickly to answer of question 10. So that means that will be the last question for today, because I'm somehow tired. So can end up here. Maybe tomorrow we continue with a series of questions. So tomorrow also we can solve around 10 questions. So for reaction 1, so they are saying if we force, we have the reaction 1 and reaction 2 for question number B. So let's move to answer. So here we have this equation, and they are saying what will happen if you do this process. If you force more hydrogen to the system. They are saying if you remove some of the ammonia, if you increase the temperature, if you lower the temperature, and if you add the catalyst. Then here the B also, they have given the reaction 1 and the reaction 2. Then they are asking, given the reaction 1 and reaction 2 below at equilibrium closed container at this temperature, predict the effect of increasing the pressure by decreasing the volume in each of the reaction. So let's see what for A. So we have number I. So if you force more hydrogen in the system, you are adding the reactant. Of course, this will favor the production of ammonia. More ammonia will be formed. II, so removing the ammonia, that means you are removing the product. So that means you are also, if you remove the product also, you favor the formation of the product. So you're going to have the reaction that produce the removed ammonia. Here also more ammonia will be produced. Then if you go to the third equation, so the negative value of the enthalpy tells us the reaction to produce the ammonia is an exothermic. If you have the negative heat which is evolved, that means you have an exothermic reaction which liberates the energy, and that reaction does not like again the energy that you are adding, because it is stable when it is liberating the energy. That means increase the temperature will not favor the exothermic reaction, so there will be a reverse reaction. Some ammonia will be used up to produce back the reactant, because in this case we have the reverse reaction because we have exothermic reaction. Exothermic reaction are not favored when you are increasing the temperature. So lowering the temperature, when you lower the temperature for exothermic reaction, it is we favor the reaction. So that means lowering the temperature, you will favor the exothermic reaction, more ammonia will be produced. Then adding a catalyst is not having any effect in chemical equilibrium. So whenever you see whether they're asking to give the effect when they add a catalyst will have no effect on the amount of ammonia. It only they accelerate or speed up the reaction, but it will not have the change. It will not have any effect on the change of equilibrium. That was question A. And question B. B, we have two different equations. Increasing the pressure, we will see it will favor where there is a small number of mole. So then in the reaction 1, you have 4 mole of reactant and 2 mole of product. So that means we have less number of mole of product. That means more product will be formed. More ammonia will be formed for the reaction 1. And for the reaction 2, so we have 2 mole of reactant and 2 mole of product which are present. So they are the same. You have 2 mole of reactant and 2 mole of product. They are the same. Then here we don't have also any change. There is no effect on the position of the equilibrium because we have the same number of mole for the product and the reactant.